You know that feeling, right? You get a new app, it feels like magic, it's lightning fast, but then a year later, it just grinds to a halt. Well, it turns out there's a secret language that developers use to predict this stuff, to know how fast their code will be in the future. Today, we're going to learn that language. We're going to demystify what makes software snappy or painfully slow.
So here's our game plan. First, we're going to nail down what we mean by the scaling problem. Then we'll get into the language built to describe it. After that, we'll meet the most common speed patterns you see all the time, we'll pit them against each other in a little race, and finally, we'll see why knowing this one thing can literally make or break an app.
Okay, let's start with the big idea here, the scaling problem. The thing is, we're not just interested in how fast a piece of code runs right now with a tiny bit of data. The real question, the million-dollar question, is how is this thing going to perform a year from now when it has to deal with 1,000 or even 1,000,000 times more data? We have all felt this. I mean, think about your photo gallery app. When you first got it, with maybe 50 pictures, it was amazing. But now you've got 5,000 photos in there, and just searching for something feels like an eternity. That lag, that slowdown as you added more and more stuff, that is the scaling problem right there in your hand. And this really gets to the heart of it. See, when the amount of data is small, pretty much any code you write is going to feel fast. It's easy. The real test, the thing that separates the good software from the bad, is what happens when that data starts to grow. Does it stay fast, or does it just fall off a cliff? So, to deal with this, developers needed a common language. They needed a way to talk about how their code might grow, to compare different ideas before they spent months building them. And that language, the solution to our problem, is called BigO notation. So what are we actually measuring here? Well, the concept is called time complexity. And I want you to forget about stopwatches, forget about seconds or milliseconds. This isn't about exact time. It's about describing a relationship, a trend. As we add more data, how much more work does the computer have to do? That's the question.
And BigO notation is what gives us the labels for those trends. Seriously, just think of it as a set of simple nicknames for performance patterns. It gives us a shorthand so we can say, hey, this approach is a flat line, but that one is a steep climb. And everyone knows exactly what we mean. It makes comparing different solutions super easy.
All right, so let's meet the main players. These are the patterns you're going to see over and over again. They're kind of like the characters in our story, from the absolute superhero of performance to the supervillain that you want to avoid at all costs. First up, we've got the dream scenario, O of 1, or constant time. This is the best you can get. It means an operation takes the exact same amount of time, no matter how much data you have. Think about it. Grabbing the very last item in a shopping list is just one step. It doesn't matter if your list has 10 items or 10 million items. It's always just one step. Its performance is a beautiful, perfectly flat line. Next, we have ON, or linear time. Now, this is probably the most common and intuitive one. The amount of work grows in a straight line, right along with the amount of data. Makes sense, right? If you need to search through your entire photo gallery one picture at a time, well, if you double your photos, you're going to double the time it takes. It's simple, it's predictable. And now for something really, really cool. O log n, or logarithmic time. This is unbelievably efficient. Instead of looking at every single item, this approach works by cutting the problem in half over and over again. The classic example is finding a name in a phone book. You don't start at the letter A, do you? No way. You flip to the middle. You see if the name you want is in the first half or the second half, and just like that, you've thrown away 50% of the book. Then you do it again with the remaining half. This is so powerful that if the phone book doubles in size, it only takes you one extra step to find the name. It's just insanely good. And finally, we get to the other end of the scale. This is our villain, ON squared, or quadratic time. This is the performance danger zone. This is what happens when for every single item you have to go and compare it to every other item in the list. As your data grows, the workload doesn't just grow with it, it explodes. It curves upwards like a rocket. This is the monster lurking behind those apps that become completely unusable over time. So talking about these patterns is one thing, but seeing them go head to head, that's where the impact really hits you. Let's actually visualize this and see how these different growth rates stack up when we start adding more data. Now look at this. With just 10 items, the difference between linear and quadratic doesn't seem so bad, right? 10 operations versus 100. Okay, but now watch what happens when we jump to 1,000 items. Constant time? Still just one single operation. Linear time is now 1,000 operations.
But quadratic, it has just skyrocketed to 1 million operations. 1 million. This table right here is the scaling problem. A choice that seemed okay with a little bit of data just became an absolute performance nightmare.
So, after all that, why does this matter? What's the real point of knowing about these patterns in this race? Well, it all boils down to one simple thing: being able to make smart choices that are built to last.
This quote really just says it all, doesn't it? The performance choices you make become more and more important as your app gets more popular and has to handle more data. An approach that was totally fine for your first 10 customers might bring the whole system to its knees when you hit 10 million. And that right there is the superpower of BigO. It's a predictive tool. It's like having a crystal ball that lets you see the future of your code. It helps you understand the worst case scenario before you've even written a line, so you can pick the solution that's not just going to work today, but will keep on working efficiently no matter what.
So there you have it. The secret language of code speed isn't some complex math formula. It's just a simple way to talk about growth and efficiency. And what's really cool is, once you start to see these patterns, you see them everywhere. Is finding your keys in the morning a slow, linear search through every pocket and drawer? Is your organized bookshelf a super fast logarithmic search? It's a whole new lens to see the world through. Which kind of makes you wonder, what's the big O of your daily routine?